Welcome everyone to the Hyperloop seminar. It's already the third edition this semester, and today we're gonna have a very interesting guest. He's actually joining from Australia right now, so it's midnight for him. But yeah, so he's gonna do two talks today. So we're gonna have a bit of a different structure. So I'm gonna introduce him very shortly in a bit, and then he's gonna have his first talk around 20 minutes, and then we're going to do a quick Q&A round. So you can put all of your questions, as always, in the Q&A button below on your screen in Zoom directly. You can also put them in anonymously, and then we try to answer all of your questions. And then, so in around 30 minutes, we're going to start the second talk and have, again, a Q&A at the end of the second talk. And yeah, so I think maybe some of you also, you can check out our past talks, always on YouTube. So we're gonna upload them on the Hyperloop seminar YouTube channel, and you can check all of those out. You can also check this one out, and probably around the end of the week. So then I think we can already start with the first talk. So we have Richard McFarlane here, and he's actually into Hyperloop since quite some time. He will talk about it himself as well. So he also worked on the white paper with Elon Musk together, and he also he has a very nice website. So it's hyperloopdesign.net. I've been looking into it a bit myself, and yeah, so I think in a way, so I saw on the website, Richard, you think the world is in need of high speed and an energy efficient travel. So that's why you also promote Hyperloop. And I see you talk about lots of different topics on your website. So you've been talking about cooling, about the choice of levitation, about different station layouts, passenger cabins, and lots of different things. So also, if you guys are interested, you can click onto his website and read all about it. And today we are actually talking about, I think, like the two main topics. Is the first one is like, what about the economic success for Hyperloop? So is it really comparable, or even can it compete to high-speed rails? And the second topic will be about the choice of levitation. So we're gonna look at the wheel, the maglev, and air skis. So with that, I think you can best introduce yourself a little bit, and then I would give the floor to you, Richard, and you can share your slides with us.
Okay, good evening to everyone. Look, I first saw Hyperloop Alpha when it was released 10 years ago in 2013. I'm an engineer and I'm a passionate designer. I'd retired from my engineering business, and I was very excited about this new form of transportation. And I was particularly excited when Elon Musk, the final page, says he wanted it to be an open source project and wanted people to contribute to it. In the early days, I was on the various forums, and then I set up this website, Hyperloop Design, which is full of ideas and technical stuff. And look, it seems now most of the developments in Europe, and well done to you guys. I've been following a few of your projects, and I'm really delighted to be able to give you a talk, and thanks so much for inviting me. I want to talk about the economics of Hyperloop and the importance of cost competitiveness. Okay. I'm going to be comparing Hyperloop with high-speed rail, and a very good project is in the east coast of Australia, between our two sort of big cities of Sydney and Melbourne. It's quite a long distance, 870 kilometers, but it's actually the world's #3 busiest air route. And it's absolute prime for some sort of transportation system. 8 million passengers per year. And there have been a number of studies on this, and the high-speed rail cost is maybe 50 billion or 100 billion or something, but say if we say 50 billion, that comes out of $57 million per kilometer for the route. And it's not a very challenging route. It's relatively flat, and I mean, there's a few hills, but there's nothing too much. But it's certainly it's been talked about a lot for high-speed rail, and I think it's a good candidate for Hyperloop. So for Hyperloop to be successful, it really has to be competitive with high-speed rail, or it will never be built. High-speed rail, since Hyperloop's been announced, they built maybe 20,000 kilometers of high-speed rail. So that's the sort of standard. And look, I've been in design projects all my life, but everything that I ever worked on always had to have a place in the market. It had to have a market position, and it would ultimately sell. And that's what paid for the research. And so my view of Hyperloop is that you've got to research towards the end product, which is a transportation system that will be built one day. So if we compare Hyperloop and high-speed rail, high-speed rail, it's an established technology, which is a real advantage. People know what it is, and it's popular, and it's compatible with existing lines and network. That's an advantage. And also high-speed rail, it's very easy to have frequent stations, a lot of intermediate stations. Hyperloop has the advantage, as we know, of very high speed and very low energy. So they're two big advantages. But the real question is the construction cost. And this is where we've really got to say, how can we build it in a way that's competitive with high-speed rail? And this affects every decision in the design process. And it really has to me, it has to be the objective of the team, is to say, how can we get this to work? So my proposal is a vacuum tube that's 2.8 meters inside, steel tube. The pod is 1.65 meters inside. That's about the same width as a minibus or a large car or a Learjet. And that's 3 seats side by side, rather more comfortable than the 3 seats you get in economy class in aircraft, but 3 seats either side, 3 seats side by side. So you get 20 seats in economy. And if people want to pay a bit more, you have 2 seats side by side, a bit more comfortable, and you get 18 seats in business class. I think the speed has to be 600 kilometers an hour. And then you'd plan on, as you build up the technology, you'd be aiming for 1,000 kilometers an hour after a few years. And the vacuum, 10 millibar, I call it a 1% vacuum. So that's 1% of the air pressure, which is 99% less drag, which is pretty useful. So this is my concept for the pod. And I'll just show you how the station works. The station's really important because we've got to have a quick turnaround. We've got to turn around the passengers really quickly, otherwise the service isn't really worthwhile. So the pod comes along inside the vacuum tube, and it goes up to the airlock there, and the airlock unscrews the power car and moves it over to one side. And then the seating module rolls out. And just notice that red thing is the clamp seal that clamps onto the pressure hull and then keeps the vacuum. And in this next one, we see how the seating modules roll out, and they're picked up by little autonomous little trolleys that carry them over to the passenger area. And this next one here, there's a number of different ways of doing this. I've sort of shown it as a carousel, but there's many different ways of doing it. Basically, the seating modules come up to the passenger area, so the seats come to the passengers, so the passengers don't have to walk. And the passengers can then spend some time getting out of the seats and the new ones climbing in. but the pod actually turns around very quickly. So I think the total time for the pod would be about 1 minute at the airlock. So it's interesting looking at this route here, 870 kilometers. The flight time is about the same as an aircraft, it's similar speed. But where we've really got to get the advantage is to get the station time down. I think including station time, we can probably do this trip in 70 minutes versus 3 hours for flying. And airports are terribly slow and they're generally a long way out of town. And so that's 3 hours for flying. And I think high-speed rail would be about 3 hours as well, which means that in a way, it's hardly worth building high-speed rail because it's going to be no quicker than flying, you know? But I think the objective of this is to combine the speed of an aircraft and the quick turnaround that you'd have like a metro station, like an underground station, where you're never more than a few minutes there. So I think this is the station that will work really well. And now we look at energy consumption and we see the real benefit of running in a vacuum tube. Actually, the 27-seat pod will use similar energy to an electric car. So a really good standard when talking about transportation energy is an electric car with 2 people in it. So if we take a Tesla Model S in this case, 17 kilowatt hour per 100 kilometers, with 2 passengers, that's 8.5 kilowatt hours per 100K. High-speed rail actually ends up with quite a similar number. 8.7 kilowatt hours per passenger 100K. And we don't have electric aircraft yet, but from the figures that we can see, most likely it would be fairly similar energy consumption as high-speed rail, I think. But the Hyperloop pod uses a bit more energy than the Tesla, but it's got 27 seats. So we end up with reducing our energy consumption down to about 1 kilowatt hour, which is an 89% saving. And today's focus is all on energy and energy saving. So there's incredible savings from this, and it just shows the benefit of running in a vacuum. So now we get to the really important one. The difficult one is the construction cost. We can see from this image here that the Hyperloop has to have these big, heavy steel tubes. But once you've paid for the tubes, and of course the tubes are a lot more expensive than the railway lines and things, but once you have the tubes, it's really a much smaller project. And you can see that this is on flat land here. And one of the big issues, and I think you mentioned it before, is landowner resistance or community resistance to a project. Nobody wants a high-speed rail going through their property or through their village. It's terribly noisy and dangerous. And the Hyperloop will be much, much more acceptable. It'll be completely safe and quiet and much easier to cross over or under it. So just on flat land, I think Hyperloop maybe has got an advantage. But now we look at tunnels, and this tunnels are incredibly expensive, and the surveys for this route indicate maybe 50 kilometers of tunnels, I think probably more, and they're extremely expensive. But you can look at the difference in size here. You can have twin tunnels with 1 tube in each, or maybe a better solution is 1 tunnel with 2 tubes in it. And the one I've shown there, it's got a little walkway underneath so that you can sort of walk along inside the tubes and do the maintenance and stuff. But you compare the amount of material removal for the tunnel and the amount of concrete for the lining of the tunnel, and you're really looking at about a 75 or 80% saving in terms of tunnels, which is an enormous saving. And now we look at the elevated sections. I think a lot of Hyperloop images show, you know, the tubes elevated all the way, and I think you wouldn't do that. You're obviously going to choose the cheapest option, whether it's putting it on the ground or underground or whatever. But when it is elevated, you can see the difference here. The steel tubes will span 25 meters just with a fairly light concrete pylon to support it. And if you're crossing a river or something, if you put the tubes one above the other, you can actually span up to about 50 meters, which is really useful. But you can see here, railways are extremely heavy, trains are very heavy, and a lot of vibration. And you see you have to have a massive concrete structure for a railway. And again, you've probably got about an 80% saving in concrete compared with high-speed rail. So if we add it up now the difficulty here is that it's almost impossible to get absolute costings for high-speed rail. And even on our project in Australia, every time they work out the cost, they get a different answer. And but what we can do quite well is that we can make a comparison between Hyperloop and high-speed rail. We can just look at the amount of concrete and the amount of steel and the amount of digging and whatever. And you can see, comparing the Hyperloop pod there, the tubes and vacuum are going to cost a lot more than the rails, but then the extra costs on top are substantially less. And so I think that your Hyperloop will probably come in at a lower cost than high-speed rail, or certainly no more. I've also shown there a Hyperloop configuration that probably is the most common one, shows really quite a wide pod with 6 seats and an aisle. It's about the same size as your A380, A320 aircraft. But it sort of looks good and it's nice and comfortable and everything, but actually your vacuum tube now is costing 5 times as much as the smaller one. And it's really, the tube goes up as a square of the diameter, of course. And so you can see it's pushing the cost to be substantially more. And I think that's not the right way to go. Okay, we'll go to vacuum now. So when Hyperloop's built, it will be the world's largest vacuum tank. And there's been a lot of people said that it's going to take a year to pump it down and cost a fortune and everything, but it's absolutely fascinating and actually a lot of work to work out the real figures for the vacuum pumping. And I've been in contact with Bush in America, who make vacuum pumps, and obviously this is one of their bigger ones. So for the 870 kilometer Sydney-Melbourne route, you need one of these pumps for every 5 kilometers of a pair of tubes. And so you need 180 pumps altogether for the whole trip. The total cost of the pumps is about 50 million, which is not a lot of money in the grand scheme of things. So, and it would then take 8 days to create the vacuum to bring it down to that, well, that 1% vacuum, as I call it, or 10 millibar vacuum. And you can work out the amount of energy, and it's obviously a lot of energy. It's 950 megawatt hours to pump the vacuum down. But what's interesting about that is that if you compare that with high-speed rail, if you were to put all of the passengers on high-speed rail that currently fly, high-speed rail would be using about the same 900 megawatt hours every single day. So the cost of your vacuum pumping down, and you've really possibly only got to do it once, is actually minimal compared with the amount of energy that high-speed rail uses. And so they're just amazing figures. And as I say, quite a lot of work to calculate this out, but it's really exciting, the results. And now cooling, really interesting. It's absolutely fundamental. Every power system has a certain inefficiency, and that creates heat. So in Hyperloop Alpha, he actually proposed using water for cooling, but he was then going to store the steam. And he had no idea of what to do with the steam. What do you do with it? And so my solution here is that so at this 10 millibar pressure, water boils at 8 degrees Celsius. And water is a fantastic refrigerant. at these low pressures. It's got very high heat of vaporization, so it's wonderful stuff. And so my proposal here is that you use your waste heat and it boils the water, and then you just let the steam out into the tube. And after a while, the tube will become full of water vapor rather than air. And that's actually great because water vapor has got a lower molecular weight than air, and a higher speed of sound and less drag. So it's actually an advantage to have steam there. If it's really chilly outside, the water would simply condense on the outside of the tube and you pump it out. But if it's warmer than that, you'd have to have condensers on the outside. And what you've got to do in the condenser is you've got to pump the water vapor up to a pressure so that it will condense at the ambient temperature. So you might have to pump it up sort of 3 or 6 times or something. And on a hot day, this will consume energy, and it might increase your energy consumption by maybe 10% or something. But on average, it won't be that high. But that's a really good solution for the cooling. And probably about 60 liters of water for the 1-hour journey. So it's not an awful lot of water that you have to carry. And so just talking about safety, Hyperloop's basically safe, but it's protected inside a steel tube and it can't fall out or fall over really. So it's relatively safe. But all of the safety challenges are completely new. They're all challenges that we haven't encountered before, and we've got to obviously take it very seriously. So I'm just going to quickly cover the main ones here. Emergency braking. Standard braking will be regenerative braking using your power systems, and probably a maximum of about 0.3 G or 0.2 G or something, depending on how much power you have. Emergency braking, we can do it at 1 G, which is the same as your car. And so it's using friction brakes onto a steel rail in the bottom of the tube. And at 1 G, we'll be able to stop in about 3.2 kilometers. And if we send the pods out at 30-second intervals, which is what I think we can do, they're going to be 7.5 kilometers apart. And so we can actually stop in half the distance of the pod up ahead. So you can't have a fire in a vacuum, which is good, but you can certainly have a battery that decides to overheat. And the solution there is to remember that we've got a power car at each end of the pod, identical. So if a battery decides to overheat, you just drop it in the tube and then drive away from it. And you've got a bit of a mess to clean up, but everybody's safe. And actually, I think that would be a wonderful solution for our electric cars that catch fire sometimes. And I think you should just be able to drop your battery in the road and then go somewhere else, get away from it. If we need to get people out, and this is assuming that we've lost our vacuum, you can have an emergency exit crawling over the front of the power car and then walk along. And I think you'd have a manhole in the tube about every 100 meters or 200 meters or something, so people can quite quickly get out into fresh air. And emergency stations, I think you need an emergency station about every 50 kilometers. And the stations should be at a town that's got some sort of services there. And it means that you're never more than 6 minutes away from a station. So this is the end of this part here. So I'll turn off sharing now and ask if you have any questions.
Thanks a lot, Richard, for the interesting talk. Indeed, there are some questions. So I would suggest we just jump straight into them. Someone from the audience is asking at first, why didn't you consider doors for your vehicle design? We have seen that the top part, the nose, is the one which is let's say, and leasing the passengers inside, what is the benefit from your smaller passenger cart compared to other concepts we have been seeing where air locking has been really on the door itself, not on the top?
Okay, well, I'll answer the first part first of all. The benefit of the small pod is that my pod is actually substantially bigger than Elon Musk's pod. His was tiny with 2 seats. So the real benefit of the smaller pod is just to reduce the cost of the tube, and otherwise the tube just gets simply too expensive. And as the pod gets smaller, you really can't move around inside it, and so you really can't have an aisle. And talking about side doors, the reason when you get on an aircraft, the reason why it takes half an hour to load an aircraft is that the doors in an aircraft are very small. And the reason they're small is that they're very complicated. It's a very difficult thing to safely seal a pressurized passenger compartment. And so the side doors, yes, you could do it, but very complicated and disastrous if they fail, which is why I went the other way, is to say that the safest way to open something is with a screw thread. You know, every pressure vessel is sealed with a screw thread. And the safest way to do it is with a screw thread. And then to get the passengers out, rather than have them walking, it might take 10 or 15 minutes to walk in and out of the pod, is to actually roll them out, roll the seats out and do the transfer in the station. So it all sort of fits together, but that's my answer to that question.
This answers the question, and this is then related to the next one, which is related to the passengers' comfort. So we have been seeing that these cards are introduced in the vehicle once after the other, but it seems that passengers have a lower comfort compared to high-speed trains, where you can walk through 2 seat lines, and then you have bathroom, toilets, and even a bar sometimes. Don't you think this is needed for a Hyperloop as well? And if not, why not?
Well, I think, I mean, the simple answer to that is that you know, I've described quite a long route in Australia, and you'd complete it in an hour, and to have people strapped into their seats for an hour is really not difficult. If it was going to take 4 hours, and then you've got a problem. But you're not likely to ever be there for more than half an hour or an hour. And we sit in our cars, we sit strapped in our cars for several hours, don't we, if we're driving somewhere? And if we're in an aircraft, we're strapped in for a long time when we're taking off, whatever. So I think it's, yes, it would be lovely to be able to walk around, but you can't actually walk around because the degree of acceleration that we need to get to this high speed, you've got to be seated and strapped in. So I think that, you know, it's a compromise. If you were to build the most beautiful pod, as we've seen, these wonderful images, yeah, they look great, they're fantastic, but actually they would never be built because they're too expensive.
Okay, so as I see, it would be a compromise between speed and then comfort, which is reflected on the distance to cover through
Yeah.
2 routes, let's say. In case it would be a longer route, it would be a consideration to take into account.
Yes, well, I think yeah, look, yeah, I think if you have a longer route, and then you can elect to stop after an hour and get out and have a cup of coffee and, you know, do what you have to do and get in, you know, carry on your journey, I guess. But it's so fast that you're not going to be sitting in it for 5 hours. I don't think you'd be in New York.
You can sit there, remain seated for the 1 hour.
Yes.
There is then another question from the audience linked to the overall cost of a Hyperloop line. Someone is asking if you took leakages into account when then computed your overall cost of the system, since these leakages are then related to the pressure level you have in the tube, and thus pump consumption and other factors.
Look, I think you can eliminate leakage. You might get a little bit at the airlocks. I think you just have to go along the tube You just have to eliminate leakages. There's no reason to have leakages. I think all of your joints of the tube, I think they would all be welded, maybe with some sort of steel bellows for expansion. But no, I think you can eliminate leakage. And one advantage, what's interesting actually, I'm describing something where the tube would actually be water vapor rather than air. And if the gas in the tube is water vapor, it's actually very easy to find out where oxygen is coming in, where air is coming in, because it's a different gas. And no, I think you can think leakage. And I mean, sure, there'll always be a little bit of leakage, but the cost of that will be minimal.
Thanks for that reply. Then it's also in the same direction. It's regarding vacuum tube maintenance. How do you suggest such a maintenance to be done? Let's say, have you looked into it maybe for the design of your tubes? And do you have an idea on how much would it take if there would be a potential leakage at a kilometer X?
Yeah, look, I think, I mean, my concept for the tube is it's just a tube with nothing in it. So there won't be any maintenance to do inside, really. I think for a catastrophic leak, like a, bomb or a truck hits it or something, you've got to have, I think you've got to have airlock doors across the tube, maybe every 50 kilometers or something, so that if part of it gets damaged, then you can block it off so that you don't have to lose all the vacuum. But I don't think that. I mean, there might be a certain amount of cleaning in the tubes. I think maybe things fall off the pods or something. And I think you can do quite a lot of maintenance remotely. You can have a little sort of remote truck that goes in there and does whatever needs to be done. But I mean, there's nothing in the tubes to go wrong, really.
Okay, so we could imagining as a tube which is has an opening at the front and then one at the end once we arrive to destination.
I'm sorry, say again.
We could imagine this tube to have two openings, one at the starting point and then one at the destination.
Yes.
Okay.
There's
Because
just an airlock at each end. Yeah.
Mm-hmm.
There may well be intermediate stations, but not too many. There might be. I mean, for this trip, I'm looking at maybe 5 intermediate stations. They're quite expensive, so you wouldn't have too many of them,
Mm-hmm. Great. Then the last two questions are related to levitation and wheels. So I would propose to leave these questions for the second talk, which is the one
yes.
which will reply to the questions. So thanks, Richard, for the first talk. We are all ears for the second one.
Okay. So levitation, guidance, and traction. Look, this is the most important decision for Hyperloop. There's 3 options, and I'm going to cover them, but this is the #1 decision. And as always, we've got to think about economics, because we have to limit the cost of Hyperloop, because if it is too expensive, then nobody will ever build it. And so I'll cover air skis first. There were air cushion trains in the 1960s. This sort of followed on from the hovercraft inventions. And there was a number of these in different countries, hover trains. And look, they worked really quite well. They achieved quite high speeds. They really failed because they were using jet engines for traction. And jet engines are terribly inefficient at low speed and horrible things. And it's really from these is where maglev really started, is that they tried to make linear motors instead of to make these go along, and then they tried to get rid of the air and use maglev instead. So they worked, but they were not successful. The Hyperloop air skis was the most extraordinary thing, and I've often wondered how it ever happened, and I think I've worked it out. I think Hyperloop started, Elon Musk's original plan was that it was actually running in tunnels in atmospheric pressure. And it's quite logical if you're running in atmospheric pressure in a small tunnel to suck the air in at the front of it and then blow it out underneath. And it would have worked. And then I think Hyperloop then evolved into being, somebody said, oh, look, why don't we pump the air out? And the problem is that if you pump out 99% of the air, you also get rid of 99% of the lift. And this is quite a simple calculation. I did it within a few weeks of seeing Hyperloop. And it was perfectly obvious that air skis were never going to work, but people put a lot of effort into it, but it was sort of kind of doomed, I think. So I'll just talk about maglev. Maglev's amazing. Probably the most beautiful one is this superconducting maglev in Japan. It's been an ongoing project for 60 years, and has never achieved any commercial success and has never carried a paying passenger. It uses superconducting magnets. They're cooled with liquid helium down to just a few degrees above absolute zero. Very high speed. It's done up to 600 kilometers an hour, and very complex and expensive. And I went to see this. I couldn't get to ride on it, but I went to see it in Japan a few years ago. What an impressive project. Absolutely fantastic. Another more recent project is Induct Track. And this uses induced magnetism into a non-powered rail. And the rail's got, it's got sort of coils in it, but it's not powered. And but it's only ever been tested at low speed. And I don't know why they gave up, but they had oscillation problems. And one of the problems with maglev is that there's no damping. And so you can get these oscillations. The mechanical system always had a certain amount of friction. And they had problems with vertical oscillations, but whether that was why the project stopped, I'm not sure. But Hyperloop Transportation Technologies is proposing to use this, but I don't think they've done anything with it. I don't think they've built anything or tested anything with it. And then Virgin Hyperloop 1 started in 2014 and disappeared last year. They've, I think they let go their staff. They claim to have a funding of $400 million, and that is an incredible amount of money. And I don't know where it all went. And they were, and you might correct me with this, I'm sure somebody there will know more about it than I do, but I think they were using eddy current maglev. And so it's quite a low cost track, which is quite appealing. It's just an aluminium rail. And then, you know, it's appealing because it's low cost for the track, but it's also very high drag. It's like going up a steep hill all the time. And you can see here, and this is a picture that I think they didn't want to show the world, but you can see this enormous wheeled pusher, 3,500 kilowatts that pushes this thing along to overcome the drag. And they did achieve 380 kilometers an hour. And I think that's slower than some of the student teams, I think, but they're a bit of a sad project really with all that money there. And the project that's been a little bit more successful is the Transrapid in Shanghai, China. Look, it is in service. It's an operating passenger service. If any of you guys are in that part of the world, have a ride on it. I haven't. I'd love to. But it was designed by the German Transrapid company. They closed in 2005. It uses inverter controlled electromagnets, and it is fully controlled. The positioning is fully controlled. It's very good stability, and it runs at 430 kilometers an hour. But look, it's just too expensive. The Chinese government built it halfway from the airport to the city and then gave up. And so it only runs half the distance. And then they went on to build, I think, 40,000 kilometers of high-speed rail. So a lovely project, and, you know, get to ride on it if you can. But look, people are very passionate about maglev, and people have got very strong opinions about it. And why is that? Well, all of our adult lives, we've been exposed to the media and the hype about maglev, and it's the future of transportation. And it's a very attractive technology, excuse the pun. And there seems to be always investment available for it, which is surprising. But it really hasn't been that successful. And if we want Hyperloop to work, we need a successful technology to use. I'm going to talk a bit about traction efficiency. With a high-speed system, you've got a real problem with traction losses, because when you start the journey, you've got to accelerate up to a very high speed. You've got to put in an enormous amount of energy to get up to speed. And then obviously if you lose energy doing that, and then you lose a certain amount of energy while you're cruising, and then you've got your regenerative braking at the end of it, and you get your losses again. So whatever traction losses you have, they count twice. You get them twice with a high-speed system. And so linear motors, you have a long stator that has coils the full length of the route. And I know the Swiss Loop one is doing their traction rather differently, but I guess I'm describing here the more sort of classic linear motor. And one of the problems with any magnet system is the air gap. And so you need a large air gap for a linear motor, because the vehicle is bouncing around and you need to have good clearance for it. And so that large air gap reduces the efficiency. And the other problem is that our modern electric motors that are incredibly efficient, but they use all sorts of exotic materials and very fine tolerances and rare earths and things for the efficient motors. But if you put that stator along the full length of the route, you really just can't use these fancy materials. You've just got to sort of keep it really simple. And so linear motors may have 2 or 3 times the losses of modern electric motors. But look, when I say that, you can never, ever get real performance data of any maglev project. If you look at maglev projects that have sort of come and gone, they all publish the very optimistic predictions of performance. And then as a project goes along, and eventually they disappear, but they never actually give you the real data. And so, while I'm talking about maglev here, if I'm getting things wrong, well, I apologize for that. So maglev, it's a wonderful technology, and I think it's got real purpose, very fast acceleration and sort of very precise positioning as well. And the Transrapid and the superconducting maglev projects show that high speeds are definitely possible, but high construction costs and excess energy consumption have prevented these projects from being successful. But so with Hyperloop, we've already got very high costs with our steel vacuum tubes, and we really can't afford to put a lot of extra cost in there. We need a lower cost solution for the levitation. John Boyd Dunlop, he is my hero. What a fantastic guy. He made pneumatic tires for his Charles tricycle in 1887. And look, it's changed the world. I don't know where we would be if we didn't have pneumatic tires. They're just absolutely fantastic. Look at all this range of pneumatic tires that have all come out of that original invention. They all work at different speeds and they have different surface and different weights and things. But what's funny about pneumatic tires, we use them every day, and most people wouldn't even regard them as being a technology. But it's actually an incredibly successful invention. So it can give a soft ride on any surface, and good grip and very low rolling resistance. So one of the purposes, obviously, of pneumatic tires is for motorsport, and in this case, land speed records. Now, this blue car on the left, this Bluebird, my father took me to see this in Oxford. I think I was about 15, I think. And I was sort of maybe wondering what my life was going to be holding. When I saw this car, I said, I'm going to be an engineer. It had a massive gas turbine engine in the middle of it, driving all four wheels. And it did 650 kilometers an hour in 1964. Most amazing car. The wheel-driven cars, really, they're getting up to close to 800 kilometers an hour. But the salt lakes are very loose, and there's simply not enough grip on the rough surface to overcome the massive amount of wind resistance at that speed. But the car that did achieve 1,000 kilometers an hour is a rocket car called Blue Flame that got to 1,000 kilometers an hour in 1970. And it's amazing. It was done with a very limited budget and obviously on the very rough surface of the Salt Lake. I've made contact with Dick Keller, who designed the car, and inquired about the tires. And he said they did many runs. They did a lot of runs to build up, sort of slowly building up to the speed. And they had absolutely no trouble with failures of the tires or with wear. So that's an amazing car. And so this is my solution for Hyperloop. It's a pneumatic tire just running on the steel tube, just on the inside of the steel tube. The pneumatic tire will give you a smooth ride. And we need that because we can't make the tubes absolutely precise. They're always going to be a bit bumpy. And then, like all tires, we'll get good grip and stability. And I think we can expect a lift to drag ratio of 500 to 1, which is pretty good. So in 2016, I went to the first Hyperloop pod design weekend, I think it was called, in Texas. And I had a stand there and I was showing off my wheels. And it was really, and everybody else had air skis and maglev and things, and they were sort of kind of laughing about this old guy there with his old-fashioned wheels. And but at the end of it, Elon Musk gave a talk, and somebody says to him, did he prefer air skis or maglev? And he says, look, keep it simple. And he came up with the most fabulous quote, and this is from a man who does achieve miracles. He says, limit the number of miracles in series. He says, keep it simple. And he recommended wheels. And I felt sort of a bit happier about that. So talking about the tire construction, so steel wheels would not be suitable at this speed. They would work for a little while, but the fatigue cracks would make them fail really quite quickly. The pneumatic tire is absolutely ideal for this, and it really shows you the beauty of the technology. The main structural element is air, and the casing of the tire spreads the loads really evenly around the wheel. And so there's no peak loads at all. The main stress is the hoop stress around the tread, around the outside. And it's a bit like a cylinder with very high pressure inside it. But it's the stress is quite manageable. And then the sidewalls have a radial stress, which is a bit less. So when we talk about materials, the tires on your car are made of polyester. And these days they have a steel belt around the outside. The tires on Blue Flame at 1,000 kilometers an hour, they were actually spin tested at 1,350 kilometers an hour before they were put on the car. They were made of polyester, which was the only material they had in those days. So a polyester tire would run at 1,000 kilometers an hour, but I think much better to use Kevlar or carbon, which are sort of 5 or 10 times better. And a much stronger construction, again, is filament winding. You can make a much stronger tire with filament winding, but it would add to the cost, and maybe it's not necessary. So one real advantage of running inside the tube is the bank angle. So when an aircraft goes around a curve, it banks and adopts the right angle so the passengers feel upright. And we can do the same thing with Hyperloop. And what this means is that if you're planning out a route, we can have the same curve radii as high-speed rail, which is a real benefit, because if you have to have bigger curves, it increases the cost of your route. And so with good passenger comfort, and when you bank like this, you just feel a little bit heavier, which is okay if you're reclining in your seat. And your railways and maglev have the problem that they can't adjust their angle of bank, and so they've got more problems with cornering. So this would be a lovely research project for people who are interested. This is a dynamometer test rig for wheels. So it's running in a vacuum tank, and you can use it for testing the tires, of course, and the surface that you're running on. You can test your vacuum systems, and you can also test your motors in a vacuum, and you can also test your cooling for the motors. So you can do all of this relatively low cost without going anywhere. And you can really test, you can find out exactly what the wheels are going to do at speed. And this would be a lovely research project. And to get it started, there's certain stock tires. So Mickey Thompson makes land speed tires rated at 950 kilometers an hour. So you can buy those off the shelf and test them. And Goodyear made land racing tires as well. But I've also put in there a bike tire. And I think that your sort of very fancy bike tires are made of Kevlar, and they've got very thin rubber, and they're very, very thin, flexible tire. They've got extremely good rolling resistance. Bike tires are about 450 to 1 rolling resistance. And I've got a suspicion that a bike tire has probably got a higher speed potential than anything else, but I'm only guessing. It would be lovely to test it, wouldn't it? And the big question, of course, is tire life. And cars, the life of our tires is 50,000 kilometers, and trucks are normally about 200,000 kilometers. But we're running on a very abrasive surface. It's made out of crushed rocks, and intentionally abrasive to get better grip. And our tires are optimized for low cost. I mean, they're very cheap, and they use the cheapest materials. And they're also optimized for wet grip. And so you have the tread pattern and then the particular type of rubber. So your car tires are, they're optimized for grip rather than life. Your Hyperloop tires be running against a smooth surface. And we don't need grip. We need maybe 0.3 G of grip for acceleration, no cornering forces. And I'm really interested in lubrication. You could actually make a tire that would never wear out. If you coated the bottom of the tube with oil, the tire is not actually in contact with the tube. It's like the metal parts in your engine. It's all metal to metal, and then they're not actually touching one another, and they never wear out. And so with some sort of lubrication, you could really increase the life of your tube, of your tires. Obviously, you're reducing the grip as well, but maybe there's a balance where you can get something that reduces the grip down to what you need and then increases the life. So, but tire life, look, we don't know. We've got nothing to base it on, and it just needs testing. Okay, now we'll talk about the power car, and there's one of these at each end of the pod, and they're screwed on with a special thread onto the pressure hull. The pressure hull is just a simple carbon fiber tube, and the seats roll in and out of it. And so there's a few different ways to do this. The way that I've shown here is that to give us the energy we need to complete the trip, I'd be putting in a hydrogen system. It's a bit like the Toyota Mirai hydrogen car with a fuel cell. And something of that same power would actually give you enough ongoing energy to get from, complete your journey. The problem is that you need a massive amount of energy to accelerate up to full speed. And then hopefully you get most of that back when you brake afterwards. And so you actually need well, I've shown here a lithium battery of 100 kilowatt hours, which is rather bigger than in an EV. So a lithium battery would do it. But a supercapacitor would be much better if they're available, and maybe there will be one day. So, is this the best solution? So we have the minimum cost steel vacuum tube. There is nothing extra in the tube. There's no coils, no rails, no magnets, nothing. This project, if built like this, is cost competitive against high-speed rail. But now the tube's obviously a very expensive part, but we don't ever need to change the tube. There's nothing in it. We don't need to change it. What we can do is to develop the pod and the wheels designs to get better and better performance. So the pod can evolve. So it's a bit like what happens on our roads. The road doesn't change, but our vehicles get better and better. So the most expensive part, which is a tube, we build it and we don't have to change it, and then we can work on the pod. So is this the best solution? I'm not sure. Be interested in your comments. So thank you.
Thanks, Richard. Also see the attendees have also some inquiries. On this note, just to the slide you showed at the very end, someone is asking if you are then using wheels. Let's say all the propulsion unit, all this weight would be added to the pod, because if we have a magnetic levitation system, you would be able to, let's say, propel the pod, meaning the propulsion would be on the track side. So this is a weight you are not loading to the pod, but instead you are deviating it to the track. Have you looked into how much of an effect would this have in terms of weight for the pod vehicle? Because going for those such speeds, this would have an effect on the tires as well, right?
Yeah, look, I don't think there's a lot of weight. I've shown a lithium battery there, 100 kilowatt hour lithium battery that's quite heavy. I think there's better solutions than that. But I don't think there's a lot of extra weight for the transportation. And the main thing is that we're just not spending the money on putting stuff in the tube. And I do know that if you've got linear motors that are powered in the track, it gets the equipment out of the pod. It makes the pod lighter. But the cost of that is just enormous, and I'm trying to keep the cost down. And I think it's just I think it's a good solution. I think it'll work fine.
Mm-hmm. So why do you think almost everyone out there in the Hyperloop environment currently is looking or pushing towards magnetic levitation systems instead of solutions relying on wheels?
I can't answer that. You guys need to answer that. I don't know.
Yeah, it's an interesting question.
Well, look, I think, look, yeah, this is a really good question. I think what you have to do, and even if you're building a little demonstration maglev thing, I think what you have to do, even if it's a track maybe 100 meters long or something, what you have to do is to build your maglev system and then see how much energy you put in to do a run along the track. And then compare it with how much energy you would have to put in to do it if it was a simple wheeled pod, right? And then you look at the capital cost, the cost of all of the equipment in your pod, if it's maglev, and then compare that with the cost of doing it with wheels. And I think that if maglev can use less energy, or if it can do it cheaper, then I think you go maglev. But if it increases the cost of the equipment, and if it increases the amount of energy, then it's probably not the right way to go.
This is a very good question indeed. To this answer, why wouldn't we consider regular steel wheels instead, compared to pneumatic tires? Because as we saw from examples such as the Bugatti Veyron, pneumatic tires are wearing out quite fast as soon as we go over 400 kilometers per hour. So this would mean we would need to exchange the tires quite regularly.
I think your Bugatti Veyron, whenever I've seen pictures of them, they're going sideways with clouds of smoke coming out of the tires. But no, the problem with steel wheels, it's sort of your first instinct is to have steel wheels on rails. The first problem you have is how do you stay on the rails? And secondly, that you just don't get the grip. The coefficient of friction is about 0.1 or something. Or less than that if it's starting to skip and bounce. But the basic problem is that when you get up to the speeds that we're talking about, the steel is so highly stressed, and it's also suffering from peak stresses at the contact point, is that it's going to fatigue and fail very quickly. And the beauty of the pneumatic tire is that it's very resilient, and the fact is that pneumatic tires have been proved at 1,000 kilometers an hour, and the fastest steel rail is 500 or something, I think, isn't it?
But the question is really durability on the long run, because ideally you would change these wheels every 100 rides, let's say, or every 200 rides, and not every 10 rides.
Look, this is the question, and we don't know the answer. And the reason that I'm suggesting this test rig, which is quite a simple project to do, is that we do not know the answer to what the tire wear will be. But you can work out a number. You can work out a minimum distance for the tires where the cost of the tires is starting to get significant against the running cost or against the ticket cost. And you're sort of getting down to, anything below 10,000 kilometers. And you can say, look, they're just not working well enough. If you're getting 100,000 kilometers, and then the cost of them is sort of insignificant. But we don't really know the answer. We can use materials like polyurethane, which are much, much more durable. They don't have the grip. So polyurethane is far more durable than rubber, but we can't use it on tires because it's very slippery. It wouldn't grip the road, So I think there's lots of options, but really we've got to test it. We don't know the answer.
Then this is related more to, let's say, the suspension system. It's related to the bearings. The question is if you have looked into bearings which are durable for such applications, and what would happen if we would have bigger masses in the vehicle if we are talking about up to 40 tons for cargo pods, for example.
Look, I think the wheel bearings, if you look at the bearings in a jet engine, you look at these big jet engines in our aircraft, if you look at the bearings in your jet engine, and they last for years sometimes, they've got far, far more load on them than our wheel bearings. And I don't know how the bearings are constructed, but our wheel bearings are very achievable, but they would obviously be cooled with, they have to be cooled with oil flow rather than grease, which is what we have in our car bearings. So I don't think the bearings are a problem. And so I'll just quickly, you mentioned a cargo pod there. I think that Hyperloop is obviously very suitable for carrying packages, and what I've described with my seating modules there, it's very easy to have one of those that that rolls in and out, but it's full of parcels instead of packages instead of passengers. That's very easy. A lot of projects are proposing carrying shipping containers, and the cost of a Hyperloop system to carry shipping containers is just enormous. It's going to cost you, what, 3 times as much as high-speed rail. And a shipping container carries, you could carry about 60 passengers for the same space as one shipping container, a 40-foot container. And a shipping container would never, ever pay 60 fares. Shipping containers, most of them come by ship anyway and take weeks to come. So I think it's absurd to talk about carrying heavy freight on Hyperloop. I think we've got to concentrate on passengers and parcels, which is no problem.
Okay, that's an interesting approach, because in terms of safety, which is implying regulations and safety aspects, someone maybe could tell that at first maybe the cargo case would be validated for Hyperloop applications before jumping into passenger transport, right?
Yeah.
Mm-hmm. Mm-hmm. Yeah, so then this would lead us to the last question. Someone is asking, how would we make sure that the pod is not oscillating up and down, since there is no guidance inside the tube?
I think, are you talking about swaying like this?
Yeah, I think so.
Well, the suspension I've drawn, and in terms of absorbing bumps, which is very important because we can't make the tube perfect, but the tires absorb a lot of bumps, a lot of small bumps absorbed by the tires. But I've drawn in my image fairly conventional, car suspension, and with springs and shock absorbers and sort of conventional stuff. But in terms of steering it, if it didn't have any steering, let's say you were to run your car along there with your hands off the wheel, the caster effect would keep the car in the bottom of the tube, but it would probably sway around and make people sick. So there has to be a steering. The wheels have to be steered to keep it in a nice straight line. And then when you get to a corner, it has to be steered to adopt that angle of maybe 30 degrees or something. So steering is really important, because otherwise people get really nauseous if it's not going right.
And the steering, would it be automatic?
Everything's automatic.
Everything is automatic, of course.
Everything is automatic. No people involved.
They only sit down and enjoy the ride.
Yep.
Yeah. Well, with this, we are also at the end of the second talk, and also at the end of the question round. So thanks very much, Richard, for taking the time and participating into the seminars. We really appreciated that. And then I would like to hand over to Andrea next week. We're getting on.
Exactly. Thank you, Daniel, and thank you, Richard, for joining in from Australia. So next week, we're going to have 2 guests again. So as always, Wednesdays, 5 p.m. Central European time. And we're going to have one talk more about also business case, a bit economic. So Krios Neyens is going to talk about spillover applications to accelerate the valorization of Hyperloop. And the second talk is actually from one of our co-organizers. So it's going to be from the Technical University from Munich, Xiao Nicolau, and he's going to talk about aerodynamic investigations of the Hyperloop system at velocities above the control width limit. So we're going to have a more economic talk and a more technical talk next week. So with that, I will wish everyone a nice evening and thanks for joining. And I hope to see lots of you next week.